curvature. So last time we did, I guess, the ellipsoid example. There is one more example. So let me just start with that one. The saddle surface. So this belongs to the actually, section 5.3, I guess, right? No, 5.4. So suppose M is the surface given by the equation z equals xy. Then we may choose a surface patch for this, like this. So, right, x is u, y is v, and z is x times v. Then x sub u, these are tangent vectors determined by the surface patch. And we had these quantities. And if you compute this, this is just 1 plus v squared. F is x sub u dot x sub v, which is in this case u times v, right? And g is x sub v dot x sub v, which is 1 plus u squared. What else? We had u, normal vector, determined by the surface patch, which is just x sub u cross x sub v, divided by the norm of this product. And if you compute that, so here are the vectors. If you compute that, this cross product is minus v minus u 1, and the length of this, what is the length of this? This is just 1 plus u squared plus v squared square root, right? So this is the unit normal vector. This surface is actually just this surface, okay? And here is normal vector, unit normal vector u. Okay, then we have what? To compute LMN, I need second derivatives. What is u sub x sub u? So I take derivative of this with respect to u. There is no u here, so this is just zero vector. X sub uv, I take v derivative of this, so it is 0, 0, 1, and x sub vv, v derivative of this expression, that is also 0. Okay. All right. So I had this quantities. L was x sub uu dot product with u. Well, x sub uu is just the zero vector, so this is 0, and similarly x sub vv dot product u is 0, so this is n. What about m? M was x sub uv dot product with u. X sub uv is this vector, so I take dot product of this with this one. Minus v times 0 is 0, minus u times 0 is 0, 1 times 1 is 1, so the result is 1 over this expression. So 1 over 1 plus u squared plus v squared. Okay, so these are the quantities. And finally, what was K? Gaussian curvature, L times N minus M squared divided by EG minus F squared, right? So L and N are already 0. I have this guy squared, so this is 1 over square of this is just this expression divided by EG minus F squared. E is this, G is this, so let me just write down 1 plus U squared, 1 plus V squared minus F squared, which is U squared times V squared. So K is just kappa, or K. So this is 1 plus U, this is U squared, V squared, and U plus U times V squared, right? U squared, V squared. U squared, V squared is cancelled with this. And then I have just 1 times, so I have 1 plus U squared plus V squared from this expression. The denominator is this. I have already one more term, the same term. So this is squared. But it should be minus because I have minus sign here. So this is also negative curvature. Negative curvature. What about the scalar curvature? H GL plus EN minus 2 times F times M divided by 2 times EG minus F squared. I mean, if you do the computation, we all know what these quantities are. If you do the computation, here is the result. So this should be minus UV divided by 1 plus U squared plus V squared and to the power 3/2. As I said last time, you know, you should know these formulas, but don't memorize them. In the exam, I'll put them on board or put on the exam paper, okay? But you should know how to use them, of course. I cannot keep them in mind, so I don't expect nobody does that. You may, of course, but you don't have to. All right, so that is it for section 5.4. Now we start section 5.5, the implicit case. So in this case, our surface is given by an equation. So let M. Again, what we are going to do, we will compute all these expressions, okay? But this time our surface is not given by a surface patch, it's given by an equation, okay? So from that equation, we will try to obtain all those information about the surface. So let this be a surface described by a single equation. G equals 0 for some smooth function. G from R3 into R. So our surface M is described by such an equation, G equals 0. G is a function, okay? Of course, where 0 is a regular value. What does this mean? This means that the gradient of G at any point is not 0 for any P in G inverse of 0, which is M. The derivative map of this function is what? It is given by just dot product with the gradient, and regular value means the derivative map is not 0. Therefore, the gradient of this, right? So G star from TP R3 into TGP R, right? G is a function from R3 to R, and I have this function. So, and this is a point in R3, but I ask that, you know, P is a regular value. Sorry, P is a, okay, 0 is a regular value, meaning that at any point in the inverse image of 0, okay, this map is onto. I want this map to be onto. And how this is given? Well, this is given as follows. You take any vector. What is the image of this? That is just, we actually computed at G, or gradient of G at P dot product V. So I want this function to be onto, okay? For this to be onto, all I need is that, you know, there is one vector so that this product is not 0. But to be able to find a vector for which this inner product is not 0, all you need to have is that this gradient vector shouldn't be the 0 vector, right? If this is not the 0 vector, you may just choose this vector to be this vector. Then the dot product will be the norm of this squared, and that's a positive number. Okay. All right. What else? I guess we defined regular value before, right? Yeah, okay. Okay. Okay, now if alpha is a curve, is a smooth curve, so differentiable curve in on M, then of course alpha prime t is a tangent vector. Therefore, it is okay. I am trying to say that this is a tangent vector. So how then? Of course, g of alpha t is 0 for all t in this interval, right? Why is that? So my curve is something like this, alpha t. This is a curve defined on some interval. And this is my surface M, which is described as G equals 0. So meaning that if you put anything on this surface, you should get 0. Alpha is on this surface, therefore G of alpha t is 0. Well, I'm sorry. Well, since this is 0, if I take derivative, t derivative of this, it will be still 0. So take ddt of both sides to get what? ddt of g of alpha t equals derivative of 0, which is 0. But what is this derivative? This is a function from R3 to R, and this is the function from R to R3. I have the composition. What is the derivative? Well, it is just the Leibniz rule. This is just the derivative of G at alpha t, dot product derivative of the inside. Okay. The derivative of this expression is equal to this. Well, this means what? This means alpha prime t is perpendicular to gradient of G, right, at the point alpha t for all t. And for all alpha, of course, and for all alpha. Well, I can choose a curve along any tangent vector, right? Give me a tangent vector at this point. I can find always a curve which is tangent to this gadget, meaning that, you know, this could be an arbitrary tangent vector. So this means what? The gradient is perpendicular to any tangent vector. So gradient of G alpha t at this point, let's say this point is P, okay, is perpendicular to any vector for any V in TPM. So hence is a non-zero normal vector to the surface M given by this equation. So the conclusion is that if your surface is a level surface of some function like this one, right, M is given by a single equation, but you want that 0 to be a regular value, meaning that the gradient of G at any point of the surface is a non-zero vector. It turns out that that non-zero vector is normal to the surface, okay? Normal to the surface. So your surface is like this. Your gradient vector is always normal to the surface. Okay, so it's always normal to the surface. Gradient of G at P. So this is a easy way of obtaining a normal vector to your surface in case it is given by an equation. All right, now let Z equals be the gradient field, and I know that this is a non-zero vector, so I can divide it by its length, so that U is a unit normal vector field to the surface. So it is just the gradient divided by the length of the gradient. Let me do a quick example, okay? Let's say our surface is given by this equation, G from R3 into R, G equals GXY, Z equals Z minus X square minus Y square. So the surface F is just given by this equation. Let's say, what is that surface? So it is just Z minus X square minus Y square is 0, or Z equals X square plus Y square. So it's a paraboloid, right? It's a paraboloid like this. Let's see whether 0 is a regular value. What is the gradient of G? Gradient of G is just, so I take derivative of this expression. Derivative with respect to X is just minus 2X. Derivative with respect to Y, minus 2Y. And derivative with respect to Z is just 1. You see that the gradient is never 0, right? So this is never the 0 vector. No matter what X or Y is, no matter what X and Y are. Therefore, actually, any real number is a regular value. In particular, 0 is a regular value. So any real number in particular, 0 is a regular value. For what is Z in this case? So Z is equal to gradient of G, which is just minus 2X minus 2Y, 1. And what is the normal field? Z divided by its length. So it is just minus 2X minus 2Y, 1 divided by length of this vector, sorry, which is 1 plus 4X squared plus 4Y squared. So this is the normal field. Yeah. This one, let's see. The Z coordinate is positive, therefore the vector should be inside, right? I mean, if it were outside, then the Z coordinate would be negative. So this vector is this one. I mean, it's normal, of course. I should be more careful. So normal vector field is this. Okay, it's pointing towards inside the surface. Well, I mean, you see, I may replace this G by minus G. So I could use this function. It is the same surface, but the gradient vector will be the opposite one. So if you just change, I mean, replace your function by multiplying with -1, you get the other orientation. Okay. So from the equation, you cannot just right away say, you know, which one is which. Of course, you know, it doesn't make sense always whether, what do you mean by pointing, you know, inside or outside. For some surfaces, even for, you know, for this one, paraboloid, we kind of think that, you know, this is the inside and this is outside. But for a hyperboloid, you know, it is not easy to say which side is, you know, inside, which side is outside. Okay, now let's continue our discussion. Let S denote the shape operator of the surface of M corresponding to this U. Okay, shape operator was the derivative of the normal field, right? Basically, so for any tangent vector at the point V, the shape operator takes the value minus the covariant derivative of U with respect to V for any vector in the tangent space to the surface M at the point P. And here P denotes, you know, P is this point. So this is the shape operator at the tangent space TPM. Okay, now Z, which is the gradient of G, has components. Let's say I from 1 to 3, Zi times Ui. Ui meaning that U1 is just 1, 0, 0. U2 is 0, 1, 0, and U3 is 0, 0, 1. Okay. Let me write Z, the gradient, in this form. Then, of course, we know what. Then the covariant derivative of Z along the vector V will be what? We had computed this stuff previously. So this is just basically V, and then you take derivatives of the components of this vector field along the vector V, and then you multiply them by Ui. And what about this expression? Well, U is the normal vector. So it is just Z divided by unit normal vector, Z divided by norm of Z. And what is this? Well, this is a vector field multiplied with a function, right? I have a function which is 1 over norm Z multiplied with a vector field. And I am taking the derivative of that expression with respect to V. Again, we use Leibniz rule. Derivative of the z times, okay, this function plus, so I take derivative of this guy. So this is, you see, this is just 1 over z times z. So I have this vector field and a function, and I am taking its derivative. I first take derivative of this and multiply with this function, and then plus derivative of this expression. Derivative of this will be a vector field, and then we just take dot product with z, right? This is how covariant derivative acts on vector fields multiplied with a function. Yani şeyi hatırlarsanız, covariant derivative f times, let's say, a vector field. This is just f times the covariant derivative of f, x, and then x dot product covariant derivative of f. But this is just yeah, this is well, you may think it this either like this, or this is of course vf. Okay, now let's see what we get. Now I have this expression. You see, no, no. I said something wrong. This is not a vector, right? This is covariant derivative of a function. This is just v evaluated on the vector, on the function, which is this one. So this is a real number. So this is just usual product, scalar product, not dot product. I'm sorry. Yeah. Here also, you know, this is a vector, this is a scalar, and here this is a scalar and this is a vector. But the thing is the following. This is a normal vector to the surface, not unit normal, but a normal vector to the surface. And then I multiply this normal vector by some real number, right? Real valued function. So this thing is a normal field to the surface, because this vector is always normal to the surface, and then I change its length with that function, right? I multiply its length, basically. The direction doesn't change, you just scale its length. Okay. So let me just write that down. The vector v of this gradient of this, covariant derivative of this, or this is just this expression, v evaluated on this function times, okay, z. So times z. This is a normal vector, is normal to the surface M, and we will denote by minus nv. So the shape operator at V, which is by definition this gadget, so it is minus the covariant derivative of Z divided by norm Z plus NV. Why plus? Because I have minus sign here, so when I put minus sign here, I will get minus of this expression, and minus of that expression is denoted by NV. So the shape operator has this expression, okay? The thing is that this is normal to the surface. Okay, now we have some remarks. So we are preparing a setup which will give us computation of Gaussian curvature and scalar curvature for an implicit surface. Remark, I should change the board. Okay. Now here is the remark. The first part is this. If W is a tangent vector to the surface, then NW, like NV, right? Here I had NV. I can choose another vector, NW. This is normal to the surface. We just saw that, normal to M, and thus parallel to NV. Hence, NV cross NW is 0, right? Okay, let me draw you a picture. I had this surface, and I have this normal vector field Z, and V is a scalar multiple of this, right? And V is something like this. What about NW? NW is another vector parallel to Z. So NW could be like this or could be in the other direction, NW. But the thing is that both of them are parallel to Z, therefore they are parallel to each other, and therefore their cross product must be 0 because they are both normal to the surface. So that's the first remark. So what we have seen is that this product is 0. So NV cross NW is 0 for any VW in TPM. For any two tangent vectors, this cross product is 0. What else? Okay, now if Y is a tangent vector field, on M, then well, Y is tangent. So Y is a tangent vector field. Y is tangent. Y cross NV. then y cross nv, right? This is perpendicular to nv, clearly is perpendicular to nv, but this is a normal vector field. If you have a vector field which is normal, perpendicular to the normal field, then it has to be tangent. So that y cross nv is also a tangent vector field. So this is a cheap way of obtaining a tangent vector field, given that you are given another, a tangent vector field. So if y is any tangent vector field, if you cross that with the normal vector, any normal vector field, then what you get is another tangent vector field. And the nice thing about this is also perpendicular to y. Therefore, this vector field is not only a tangent vector field, but it is perpendicular to the original vector field, so that y and y cross nv form a orthogonal basis at each point. Okay, let me erase this board. So you get two vector fields tangent to the surface, and those vector fields are orthogonal to each other. Since y cross nv is also perpendicular to y, we see that the tangent fields, the tangent vector fields y and y cross and v form a basis, form an orthogonal basis for the tangent space TPM at any point P on the surface. Of course, I want this, provided that YP is not zero. I mean, if your tangent field is zero, then of course you cannot get a basis, right? If this is zero, this will be also zero. So you get two zero vectors. But if it is not zero, then if you have one vector field, you get another vector field, and they are very, nicely situated. They are always orthogonal to each other. Okay. In particular, they form a basis. Okay. Now, we state the following lemma. All right, so let me erase the board, this board, which tells us how can we compute the curvatures using this machinery. All right. All right, so I changed the board again. Now here is the lemma. Okay. Let Z be a non-vanishing So it is not zero at any point. Normal field, vector field on the surface M. If your surface is given by an equation, G equals 0, then Z is just the gradient of G. If the 0 is a regular value of your function, of course. Now, if V and W are tangent vector fields, so V and W could be Y and Y cross and V, for example. Okay, such that their cross product is your normal vector field, then the Gaussian curvature is just Z dot product, the covariant derivative of Z, cross product covariant derivative of Z with along W. So you take covariant derivative of Z with respect to V and covariant derivative of Z with respect to W, and then you cross product the results divided by norm Z to the power 4, and H is this, the scalar curvature, minus Z, and then covariant derivative of Z cross product W, the same expression, V cross the covariant derivative, yes, divided by 2 times Z cubed. Okay. Okay. Now let's see the proof. Yeah, I think we may erase the board. Okay, but I have only 1 minute left. Let me stop here. In the second hour, we will prove this and then do some maybe examples. All right, so let me stop. Kaydı durdur.